Okay, so we've already talked about the two notions of addition and subtraction amongst vectors, and when you add or subtract two vectors, the result is another vector. Today we're going to talk about a notion of multiplication of vectors, and there's kind of two different ways to get at multiplying vectors. One of them is called scalar multiplication. And scalar is just another word for a real number that's not a vector, and we'll write that down. So it can be any number. Scalar is just a number. And then the dot product. And the dot product is behaves a lot like multiplication. It has a lot of the same properties that multiplication has, but it's not exactly the same thing. It's a little bit different. So we'll first go over the scalar multiplication part, which is pretty straightforward. And the dot product has a little bit more meat to it and more usefulness to it than scalar multiplication has. But we want to cover both of these. So let's define scalar multiplication first. So suppose U is a vector. And C is a real number. Then the vector CU has magnitude. This is like C times U. Has magnitude absolute value of C times the magnitude of U. So what this is basically saying is that whatever the vector U is, make it C times longer. Make the magnitude C times greater. And this absolute value is to say that, well, C could be a negative number, in which case, how does that affect our vector when we multiply them? Well, that's if C is positive, then the vector CU has direction, we'll say this, has the same direction as U. And if C is negative, then CU has the opposite direction. As U. Okay. And so that's our notion for scalar multiplication. You get another vector when you multiply a vector by a scalar. The vector that you get is C times, has length C times the length of the initial vector, and it has either the same direction or it has the opposite direction. Okay. So let's sketch a picture of this. Let's get this set up. Let's sketch a picture of this in action. What does scalar multiplication look like? Well, it behaves exactly how you'd think. Example, sketch the vectors we'll call V equal to, let's say this. Start over. Suppose V is equal to, let's do the vector 1, 2. Sketch V 3V and negative 2v. Let's do those three vectors. Thank you.
Welcome.
Oh my goodness. Thanks, Julie. Okay, so the vector v is from 1 to 2. That's our vector v. I'm going to sketch 3v in red and negative 2v in green. Let's do that. Well, let's do this one in blue. Because we got 3 colors and we're dealing with 3 vectors, we can do 3 different colors. So blue is my original vector v. So what do you expect happens to 3v if it's 3 times longer? Well, we take this arrow and we have 3 of it stacked on top of each other. So 3v is going to look like a vector that goes from 0, 0 all the way to 3, 6. That's 3v. Same direction as the original vector, it's 3 times longer. So you can see that this arrow and then this arrow and this arrow all add up to the same length. There's 3 of them. And then negative 2v would be pointed in the opposite direction. So let's draw that vector. So opposite direction means we're going down and left. And this would be going negative 1v, so I need to go down and left again. This is negative 2v. And so what are the coordinates for for the other vectors 3v and negative 2v? Well, since we're going the same distance right and up 3 times for 3v, then this one is 3, 6, which is 3 times 1 and 3 times 2. And for the green vector, since we're going down, left and down, left 1, down 2, left 1, down 2, then the resulting vector negative 2v is going to be negative 2, negative 4. Let's see if we can see that. Yep. Okay. And so let's create a rule for what scalar multiplication does to the components of the vector. Because it seems like it just takes the components and multiplies them. So going back to our original piece on vectors, or from earlier, if v, well, let's say u is a vector equal to ab, and c is a real number, then cu, the vector c times u, is just equal to ca, cb. Your homework assignment will have you show why this is true using the original definition. So then you've got to bring the cosine and sine pieces into it to show that this is true. But this is another way to get at scalar multiplication. It multiplies the first coordinate and multiplies the second coordinate.